Hey everyone, welcome back to my YouTube channel. Please subscribe if you're new here. Okay, so in today's video, we're going to be discussing about quicksort in Haskell. So quicksort is a pretty cool algorithm for sorting. It's a very clever algorithm in a way that it takes upwards of 10 lines to implement quicksort in imperative languages like C, Java, etc. The implementation of quicksort in Haskell is much more shorter and elegant. Quicksort has become a sort of poster child for Haskell. Therefore, let's implement it here, even though implementing quicksort in Haskell is considered really cheesy because everyone does it to showcase how elegant Haskell is. Okay, so what should be the type signature of quicksort, a function in Haskell? So basically, let's define a custom function called quicksort, which we are going to use to sort the list of items which we're going to passing as input, and which is supposed to return to us the sorted list of items. So the type definition is simply a list of items of type A, and it returns a list of items of type A. So it takes input as a list of items of type A, and it returns a sorted list of items of type A. So what is this A? So A should be a instance of odd type class. Why odd type class? Because only elements which have ordering capabilities can be sorted. Because Haskell needs to know which comes, for example, let's say 10 is bigger than 1. So in sorted list, if it's in ascending order, 10 should come after 1, like that. So this odd type class is going to tell Haskell that A is of a A has a feature in which it we can sort it out. Okay. So now what would be the edge case in this? And so as you might already guess, sorting in Haskell is going to be implemented using recursion. So for recursion, as we know, there should be a base case and a recursive call, right? So what should be the base case? The base case, let's say, is the edge case. So what is the edge case? Suppose let's say I pass an empty list into the quicksort function. It should return me the empty list itself. That is pretty much the edge case as well as the base case. So let's code it up right here. Quicksort empty list, return empty list. Okay, now let's try to understand how quicksort really and actually works. Okay, so let me just clear it out. Okay. So let's take an example question and understand how quicksort really works. Let's take this following list as an example: 5, 1, 9, 4, 6, 7, and 3. Okay. So in quicksort, if you already know a little bit about quicksort, you know about something called a pivot. A pivot can be literally any element from this list, and which I can select. Let's say I'm selecting this element 5. I'm randomly selecting it, and now why I'm choosing 5, I will be mentioning it to you in short period of time. So I'm going to place this 5 over here, and I'm going to concatenate it with two other lists in front and back. So what should be the elements in back? So this right hand side of 5 should be filled with all elements greater than 5. And what should be the left hand side of 5 be concatenated with? Should be all elements less than 5. So what will be our result? 5 concatenated with. So what are the elements greater than 5? So 5 is the selected element, 1 is not greater than 5, 9 is of course greater than 5, 4 is not greater than 5, 6 is greater than 5, 7 is greater than 5, and 3 is not greater than 5. And what are the list of elements which are less than 5? 1 is of course less than 5, 4 is less than 5, and 3 is less than 5. And what I'm going to do is I'm going to recursively call this quicksort function in these both lists, and I'm going to keep this 5 as it is, right? So what will happen? Here I'm going to have to select a pivot element randomly, but I'm going to select 9 over here, which is the first element, and here also 5 is the first element. Why am I choosing the first element? I will explain it to you shortly, but you can choose literally any element and stick with that element last or the first or the middle, anything, okay? But I'm going to stick with first element, and the reason is pretty easy. I'll explain to you when I'm coding it in Haskell. So again, I'm going to have to choose 9 over here and concatenate it with two things. So here it's going to be all elements greater than 9, and here it's going to be all elements less than 9. Remember, we are passing this list into the quicksort function, so all of these are, the function is currently not aware of all these things, right? So the result will be function less than 6, 7, and then basically no elements greater than 9 here. So it's going to be an empty list. Right, so I just adjusted the screen to accommodate more space. All right, so now we see, as I told, I'm going to again recursively pass these both lists into the quicksort function. And notice here, this is an empty list. So notice in the function, if you recall properly, the empty list was our base case or the edge case, and it's simply going to return an empty list, and that's going to be the end of it. And notice here, I'm not calling the quicksort function in these elements, so that is also going to stay as it is. And let's continue. If you feel free to pause the video and try the remaining by yourself. Oops, should be 1. And what's going to be on the right side? All elements greater than 1, 4, 3. And on left side, all elements less than 1, which is nothing. So this, again, I'm going to pass into the quicksort function. So remember, at each time I'm calling the quicksort function twice. So keep that in mind. It will be helpful for us while implementing the coding part. So this is simply going to return to us an empty list, and this 1 is going to be as such. And we come down to 2. So we pass this list. We're going to take the 4, which is the first element, as our pivot, concatenate two things, all elements greater than 4, which is basically nothing, and all elements less than 4, which is 3. And I'm going to pass this again to the quicksort function. And what about this function? So I'm going to select the first element as our pivot, 6 plus 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 plus, and our elements greater than 6, which is 7, and the elements which are less than 6, which is nothing, like this. And I'm again going to call recursively the quicksort function on these two things. So this is going to return an empty list, and this is as well as going to return an empty list. And 3, as we know, is again going to make the pivot as 3, and going to recursively call to empty because quicksort function with empty list, so it's again going to return an empty list. So finally we'll be having this. We have 1, 3, 4, 6, 7, 9. Oops, there's a 5 over here, and this is our sorted function. This 5. Now how to code this up? So let's say quicksort, they're passing something which is other than an empty list. So we are gonna split it up into x and x's. So x is basically going to be the head, and the x's is going to be the tail. So why did I choose the first element as the pivot element always? The answer is pretty simple. I can use head function in Haskell to get the first element. So I can easily get the pivot each time. So here I don't need to use the head because I'm getting it in X itself. And so what is going to be the result? So we are going to keep the X in the middle, the pivot in the middle, and concatenate it with two other lists. So what are they? They are the smaller and the bigger. So now there's a bit of ambiguity here in the sense that Haskell doesn't know what is smaller, what is bigger. So for that, let's use a let in condition. Let smaller equals to bigger equals to in this expression. So what is smaller? Let's use a set comprehension a such that a belongs to xs, which is basically the tail of the list, and here also a such that a belongs to the tail of list, but there's a condition: all elements in this smaller should be less than x. So we add a condition: a less than or equals to x, and the bigger, all elements in bigger should be strictly greater than x, right? And now there's a problem: we are not recursively calling the quicksort, so we must recursively call the quicksort and here as well. Wait. Now, notice here we are calling quicksort here twice. So we can use a more optimum method where we sort the list here itself. So smaller sorted will be quicksort, bigger sorted will be quicksort, and we can just simply remove this, and there we go. We have our quicksort function fully implemented. So let's load this function in GSCI and let's run it. Quicksort. Let's take our example 10, 2, 5, 3, 1, 6, 7, 4, 2, 3, 4, 8, 9. And there we go. But notice here we are not explicitly mentioning A is an integer type, so we can basically use it with any a list of ordering capabilities. So for example, let's say the quick brown fox jumped over the lazy dog and hit enter, and there we go. We got a listed, a sorted string. So a string, as you know, is a basically syntactic sugar for list of characters. So that's why this is possible to do so. I hope you learned something new in this. Goodbye.